Okay, so today we're going to look at combining more rational expressions. In the last lesson, we looked at combining rational expressions when you either had division or multiplication involved. So now we're going to look at combining rational expressions where you have adding them together and combining them, or subtracting them and combining them. As I told my class today, I think this is kind of one of the most important lessons of the entire year in Algebra 2. It's extremely common to see rational expressions that need to be smashed together, whether you're adding, subtracting, or dividing. Adding and subtracting are really, really common in terms of various things in calculus. So a very important lesson. So let's get right to it. To do these first couple problems, I don't think we're going to have much trouble. The reason being, if you look at them for a second, I think they're just problems, rational expressions with the same denominator already. They already have a common denominator. So if two rational expressions already have a common denominator, you shouldn't have any trouble combining them. It's essentially the same as doing stuff like you've done since, I don't know, from 4th or 5th grade, where you had things like, 1/2 plus 5/2. If you've got 1/2 plus 5/2, the things are already the same. What you have is 1 plus 5/2. So the 2 stays the same on the bottom, and you go 1 plus 5 on top to get your 6/2, which reduces to 3. So I mean, this little example here I think has a lot of ideas in it that we're going to use. Once you have a common denominator, write that denominator once, put the things together on top, do any like terms. These are of course like terms, 1 and 5. And then there's also this idea of simplifying at the end. I think that we've got all those things in rational expressions as well. So let's look at these first two problems. So the first problem, we've got a common denominator already. So just like that last one, we're going to say the answer is going to be having that same denominator, and all we've got to do is put the stuff together on top in terms of like terms. So up there I think we have 3x and x, so that's x squared. You know what, I'm going to change this problem. Let's say I wanted it to come out nicely. Let's say we had let's say we had 2x there instead. So then we're going to have 2x here. 2x and x is 3x minus 10, and x minus 2 on the bottom. So there you go. Let's try that with this one. So now we've got a rational expression minus another rational expression. Again, they have the same denominator. It doesn't matter how complex or how simple the denominators are, the same rule applies. So we're going to come over here and say, all right, the denominator is shared. They both have that same denominator of 7x squared plus 8. So then we go on top and we go x plus 7 minus x plus 20. Right? So if you were like my class, then they spotted me and kind of yelled at me at this point. That's a really bad mistake. That's what I call in my class a fundamental algebraic mistake of infamy, in fact. Because I'm not subtracting the whole thing if I leave it like that. This says subtract all of this rational expression. So in rational expression land, you can always put parentheses on the tops and bottoms of any of these parts. The one that really needs it is right here though, because that minus needs to be distributed. So that is very, very important. This problem's totally wrong unless you have a negative 20 here. So very key to avoid that. So what do we have? X minus x goes away on this one, and we've got 7 minus 20. That's going to be negative 13 over the denominator. Okay, so let's talk about both of these. So some of your problems, of course, like in the last assignment, are going to say specify the places where the expression is undefined. So where is this expression undefined? So you might not be able to guess, so you might want to try solving it. So you might say 7x squared plus 8 equals 0, and seeing if there's any place that the bottom is 0. So if I do that, I'm going to get this, divide by 7, get negative 8/7. And when I square root both sides and go square root, plus or minus, I have the square root of negative 8/7. You should see that and think back to things we've been studying. If you have a negative number inside an even root, remember that's going to be imaginary. So this has no real solution. So there's no real solution to that. So in other words, this guy right here is undefined nowhere. So if we were to specify the domain, which in your assignment, whether the book says so in your problems or not, I'd like you to write the domain. You can write that in two different ways, I don't care which. You can write it with interval notation and say, well, everything works, so you could say negative infinity to infinity is the domain of that function. Or you could use set notation and say the set of all x values such that x belongs to the real numbers. Any real number will work, in other words. You have to pick one of those notations and write the domain whenever it says undefined in your problems. So the book might not say that. Make sure you write out the domain in one of these two notations. So let's go back up to this other problem and try to write its domain. So of course we can't plug in 2, right? I think you should think for a second here. The top of this one should jump out at you as something you can simplify. So if you look at the top, I think that factors, right? This one just happened, coincidentally, to factor. If we look at factors of 10, 5 and 2, for instance, positive 5 minus 2 adds up to 3. So this guy totally factors. And in fact, this one cancels down. So we can chop off that whole piece, and this combination of rational functions that we started with simplifies to just a line. Now, when we get to graphing these functions later this week, you'll see that this cancellation part actually does contribute something to the line. So even though a line has a domain of infinity to infinity, this line's special because of that cancellation. So the domain of this problem to begin with is everything except 2. If you put 2, you get top, 0 on the bottom and top. So we've got to skip 2. So everything up until 2, or everything after 2. So you can write it like that in interval notation, or in set notation you can say the set of x's such that's this vertical line, x is not equal to 2. That says everything except for 2. Let's look at some more combinations where the denominator is not the same now. Okay, so here we have 3 more combinations of rational functions. So the first 2 ask us to subtract the rational functions. So when they don't have a denominator that's the same, you want to shoot for making that denominator the same. This is the most important part of the lesson. So first you might want to think about, are any of the pieces factorable? On this first problem, I think you can pull a 2 out of the top if you like, and you should recognize difference of squares right here. So I'm going to replace that with its factored form. So what is x squared minus 9? I think x squared minus 9 you can rewrite, so you can do another step or just erase on your problems. That's x plus 3, x minus 3. So now you should look at this problem and say, hey, those 2 pieces, this is problem 1, let me clarify here, this is problem 1, problem 2, problem 3. So in problem 1, the 2 terms share the x plus 3 already in the denominator. So if this guy just had the x minus 3, you'd have a common denominator, right? So just do it. Just be like, okay, I'm going to multiply this denominator by x minus 3. But you can't just put that blue stuff there arbitrarily. You have to compensate. You have to also put it on top. So remember, the reason that you do that is because now this, when it's multiplied, is multiplied really by 1. That is a clever 1. And that's how you want to think about it. It's a clever 1 that makes the denominators be the same, so that then on the next step I can say this is equal to x minus 3, x plus 3 is now the common denominator, and then I just see what happens on top. So I've got this stuff here, and over here I probably want to distribute. I've got a negative outside, so be very careful with that negative. So I'm going to pull this negative down right here. That's that negative. And then inside I'm going to expand this out. So I think I've got x squared and a 5x and a negative 3x and a negative 15. So I'm going to keep simplifying a little bit. So I've got 2x squared minus 30. Distribute my negative, that's negative x squared. Let's put these together inside first. What's 5 minus 3x? That's 2x. So when I distribute the negative, I get minus 2x. Minus minus makes that 15 a positive. So be very careful about distributing your minus. It's going to get you if you don't. And then any like terms up there, yes, I have some x squared. So that's 1x squared together. Got minus 2x Negative 30 and positive 15 is minus 15. Alright, so I finally have this simplified pretty well in terms of it's a single rational expression, but look at this thing on top. Before you quit, you should always say, can I factor any more pieces? And I think this guy actually factors again, right? 15 is 3 times 5. 3 times 5, is that going to give you 2 somehow? Yeah, I think it will. I think we can go x plus 3x minus 5. That times that is negative 15. 3 minus 5 is negative 2. Totally get factored. And the reason I wanted to do that is because sometimes, not always, but sometimes you can then get some additional cancellation. So this guy is x minus 5 over x minus 3. If we were to write the domain, we could write it by saying the set of values x such that x is not 3 and also not negative 3. Or we could say negative infinity up to negative 3, or negative 3 to 3, or 3 to infinity. So that'd be 2 ways to write the domain out. Let's look at number 2. I'm going to do some erasing here to clear up this space. Okay, so if we look at number 2, let's see, any factorization. That one's pretty simple, pretty simple. Pretty simple. I might pull out a 2 up there. You know, I think I'm going to write this as equal to, I'm going to pull out a 2 up here. That might be useful. And then this guy factors as 3 and 3, isn't it? That's a perfect square trinomial. 3 and 3 is 9, plus 3 and plus 3 is 6. Ah, see, factoring first paid off here because, look, I can totally already cancel out one of those guys. So this is a pretty nice problem because now, look what's left. This already has a common denominator in this case, so I don't even have to do any clever one to fix it up. So I can just say, hey, it's already got a common denominator. Got x plus 2 totally done right there, undefined at negative 3. And that's it. Let's look at one with 3 pieces. So this guy has 3 pieces. So is there anything that we can factor right away? Ask yourself. Simple, 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 different squares. So this guy I'm going to replace with x plus 3 and x minus 3. Okay, so now let's have a look. So let's see. If we want one common denominator, what's it got to have? Well, it's got to have a plus 3 from that one and that one. This one needs a minus 3. Oh, and this one, it needs an x, so I'm just going to put an x right there. So then you've got to fix up each piece. So this one has those 2, but it's missing the x. So I'm going to have to go times x times x. This one's missing the x and the x minus 3. And this one's missing the x minus 3 and the x plus 3, which is really just x squared minus 9, right? That's really just x squared minus 9, so I did a little shorthand there. So let's see what's left. Now those all have a common denominator. On this one we get negative 4x as the numerator's contribution. Over here I don't really need this 1, I don't think. So I can just distribute x squared and minus 3x. I've got a plus, so I don't have to distribute a minus. And I've got a plus here too, and I don't think I need that 1, so it's just plus x squared minus 9. All right, doing a little bit of simplifying. Let's see, we've got 2x squared, negative 7x from this and this, and minus 9. Okay, so there's that guy factored out. But ask yourself, again, is it finished? Well, the bottom's pretty finished. Those are all nice factors, nice linear factors. The top might factor. So let's look at factoring the top. And I think you have several problems in your assignment where you're going to have to apply this a not equal to 1 factoring algorithm that we learned earlier in the year. So that's definitely an important thing to know how to do by the time you're done with Algebra 2. I teach it to my Algebra 1 students, and by the time they're done with Algebra 2, I kind of expect them to know it. So let's see, how do you do that? So here's some review. How can I factor this top guy? If it factors, remember there's no guarantee, but I think this one does factor. go 2 times negative 9, you get negative 18, and then you think about factors of that, which give you the middle, very similar. So negative 9 times 2 is going to work. And then remember, you leave the outside parts alone. And you rewrite the x using this special combination we came up with. And it'll totally work in this way. I like to kind of put this 2 over with that 2 because it kind of shares something more naturally than you might otherwise. And see how the 9 will go with the 9. So I'm going to turn this around. It would totally work the other way as well. But this will make it a little easier to see, I think. So that's step 1, figure out the combination. Step 2, use the combination to rewrite the middle x term cleverly. Step 3, think about it as being cut down the middle and do what they share on both sides. These share a 2 and an x. What's left? Another x and 1. These share a negative 9. What's left? An x and a 1. And now finally, step 4, you know if you did it right or not. If this factors, then these should match every time. So these 2 big terms, they share the whole chunk or quantity, x plus 1, 2x is left, and negative 9 is left. So that's factored. So over here, my rational expression, I can write this as x plus 1 times 2x minus 9 over the bottom. And I can check for any additional cancellation, which didn't happen this time, but it will happen often. And you have to be able to factor this guy on top, because otherwise you're not going to be able to do some of the graphing procedures that we look at in the next lesson. So one more issue intimately involved with combining fractions is this idea of a complex fraction. So if you have a complex fraction is a fraction involving 1 or more fractions in the top or bottom. So they can be pretty sophisticated. These 2 examples are not too sophisticated, I don't think. So let's have a look at them. And this first example of a complex fraction, I think we've already seen problems like that. In fact, they looked like this in the previous set of work that we were doing. So when you look at this, it's another way to write this is just like this. So in the previous section of our book, I think that they were often written like this. This and this mean exactly the same thing. So you already know how to do and simplify this problem, I think. So remember, when we did this, you do that copy dot flip. You divide, when you're dividing by this guy, you have to flip it, copy dot flip to simplify. So let's do that here. So my main advice when you're doing complex fractions is number 1, make the main fraction bar much larger so that you're clear about what needs to be flipped and what doesn't need to be flipped. I think that's really key when you get into more sophisticated complex fractions. So this guy is going to be equal to, we're going to leave the top alone, and we're going to flip the bottom guy. This is pretty much how you'll see complex fractions from now on, by the way. That little division sign kind of goes away in more advanced math. So if we do that, oops, I think I made a mistake. This should be over 25, shouldn't it? There we go. Then I think we're done, unless we can simplify. So ask yourself, do any of these parts simplify? Well, 100 over 25 is 4, right? So I think these will cancel out to 4 over 1, so we can put a 4. Does anything else simplify? I think this does. So some of your problems might not simplify after this step, but this one does. Those share a 7, so I'm going to pull out a 7. X is left, 1 is left, and I've got x minus 1 on the bottom, which even though this looks like a separator, this is all one chunk, so you can cancel that out because it's 1. So this guy actually simplified all the way down to 28. So pretty simple, a lot more simple than the original complex fraction of that one. Okay. Let's look at something a little more sophisticated. So here we have a fraction with a fraction here, 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 all over the place. So follow my advice. First, make your main fraction bar much larger. And then if you have multiple fractions on the top and bottom, you want to make common denominators with those first. So up here, you need a 16 and an x. This guy's missing the 16. There's a clever one. This guy is missing that x. Another clever one. On the bottom, the common denominator is 2 and x. This guy's missing the x. x, and this guy is missing that 2. So there you go, a bunch of clever ones. So before we flip, we're going to make this nice and common denominator on top and bottom. On top, the common denominator is 16x. We have 16 over there, minus x squared here. On the bottom, common denominator is 2x. We have x there, minus 4 here. And now we can go ahead and flip that once we have one fraction over another. Here's the main fraction bar. So I'm going to have 16 minus x squared, 16x, and 2x is going to go up here, and x minus 4 is going to go down there. If you can see, I flipped that over. So the question is, does anything cancel at this point? Yeah, I think a couple things do. The x's here go away. 2 over 16 goes to an eighth. So there's an 8 left. That's all gone now. And I think if you're awake and alive, this should also look familiar. I think this is difference of squares. What's the first thing being squared? 4. It's a difference of squares, so minus plus. Second thing being squared is x. Difference of squares can be factored backwards. That kind of looks backwards, but it totally can be factored backwards like that. So at this point, you might be tempted to cancel here. And that's a good temptation, because these are kind of the same, but they're really not. That x is negative, that one's positive. You've got to factor out a negative, I think, on top to make this work. So I'm going to pull a negative out of this one. I make that x positive. I make that 4 negative. That's what I did, is I factored out a negative on top. I'm going to leave the other part alone. The reason I factored that negative out on top is because now this will indeed cancel. Now I can definitely cancel that part out and simplify it just a little bit more to become negative quantity 4 plus x, and on the bottom I just have 8. So that rational expression simplified quite a bit from the original complex fraction up there. Hope you found that useful. See you next time.